Swayam Prabha. Digital India. Educated India.
In this video, we will just summarize what all we have seen in week 5 and also what we did not see in week 5, and just to give you a preview of next week what we will be doing. Okay. So, what we saw was when you have a linearly separable classification case, that is, if you have data points which can simply be separated by a line such as this data set. In such a case, you could use logistic regression. Logistic regression or binary logistic regression can be used when there are just two classes, and the same idea we saw could be extended to k classes using multinomial logistic regression. In both these cases, the major differences were simply in the forward model. The forward model for logistic regression was sigmoid of w dot x, and for multinomial logistic regression was softmax of w dot x. Now, apart from this, we also had our loss function, which was the binary cross entropy loss function for logistic regression, and in the case of multinomial we saw that it was a simple extension, it was a general cross entropy loss function there. In both these cases, it was fairly straightforward in calculating del j del w. It turned out to give us the same expression as before, which was y minus y hat times x summation from I equal to 1 to m. Now, this followed our general machine learning paradigm, which is you take x, guess a w, get a y hat, back propagate. Okay. So, this is what we did in both logistic as well as multinomial logistic regression cases. There were these, when we tried this for XOR, we saw that it needed an extra layer in the middle. It is not possible to simply take an input and map it directly to an output without a hidden layer. However, with an extra layer, it is possible, it can be proved that you have the universal approximation theorem, which says that any function can actually be approximated to an arbitrary degree of accuracy, provided you are willing to increase your number of neurons. It is possible to approximate any function to an arbitrary degree of accuracy using one single hidden layer. Okay. Neural networks, however, use more than one hidden layer, and there is some disagreement on in the literature on this. More than one hidden layer, and this is what is called deep learning. Deep learning simply means greater than one hidden layer. That is typically what is called deep learning. There is some disagreement in the literature on this, on how many layers should you take, or should you even just make do with one hidden layer. Okay, some people are of the opinion that with certain tricks you can get by, but generally the observation is you get fewer neurons and fewer weights the deeper that you go. Now, in order to train a deep neural network, you need our back propagation algorithm, of which we saw the rudiments in the previous video. Now, one thing that tends to happen is, if you recall, our expression was delta L plus 1 was delta L times W times G prime Z. Now, notice this term G prime Z. When you have a sigmoid, this G prime or the slope of the sigmoid can actually get small. Okay, the further and further away you are from this central portion which has high slope, the further and further away you get, this can get very small and it can keep on multiplying. Okay, so, you have delta 3 is some small number, let us say 0.1 multiplying delta 4, delta 2 will be that small number multiplying delta 3, so on and so forth. So, if these small numbers keep on multiplying, it can actually get very small and it can go below a machine epsilon, and the network will what is called, it will not train. Okay. Similarly, here too it will stop training. This is called saturation, that is your value is so close that your slopes are very low, and this is the problem, fundamental problem in training deep networks. You tend to get one of two problems which you will also see in the next few weeks, which is either of exploding gradients or of vanishing gradients. That is, W actually completely blows up, of which we saw a few examples even during linear regression, that was due to improper gradient descent. Okay. Or you could have something which you think should train, but it does not train, and this is where a lot of neural network research stagnated. So, there are tricks in order to do this, and you will see Dr. Ganapathy will discuss several tricks for this in the context of convolutional neural networks next week. What is it that we did not cover? Okay. So, one was this, other things that we did not cover and which we will be looking at the next weeks is, how do we initialize W? As we saw, even for logistic regression or neural networks, the minimum is not unique. Since it is not unique, how you initialize actually has an effect on how your neural network trains. Second thing is, how do we determine the number of layers, number of neurons per layer. Okay, I just showed something arbitrary here. Both these are also hyperparameters. Remember, in addition to alpha, which is your learning rate, and lambda, which is your regularization parameter, number of neurons, number of layers per neurons, all these are also treated as hyperparameters, and hyperparameter optimization is a big problem. It is an open problem in neural networks. Dr. Ganapathy will be discussing a few details about this later. Finally, what nonlinearity do you use? I showed just one, I showed sigmoid. But there are other possible nonlinearities that people use. Okay, one is tan h, which is very similar to the sigmoid, and instead of going from 0 to 1, it goes from -1 to 1. Another possibility is something called rectified linear unit. In short, it is called ReLU. It is completely flat at one end and then it is simply linear. Okay. Now, different choices can be made for different problems. As a very simple rule of thumb, for problems with numbers, we tend to use artificial neural networks and we tend to use tan h instead of sigmoid. For convolutional neural networks, we tend to use ReLU, which you will see in the next week. So, these and other issues we will be seeing in the following weeks, and a final heads up for next week, we will be moving to what is called convolutional neural networks. Also called CNNs. They are a special case of ANNs or artificial neural networks or deep neural networks that we just saw for vision problems. Is there any problem with ANNs that we cannot use it for vision problems? No, not really. The only issue is that, let us take my favorite example, that of a 60 cross 60 image. Let us say you have 3600 features, this is just linear features, and suppose you have 3600 in the next layer also. So, you can see that this is 3600 square weights already, which is a huge number of weights, and vision problems deal with large images. So, you will have very large features, which means you have to deal with a huge number of weights. So, instead of doing that, a trick is to use what is known as convolutional neural networks. We will start seeing that from next week. Thank you.